Hello and welcome to everybody. I'm quite surprised that we have quite a few online. I thought there were only going to be two or three people. Thank you. This is a first in a series of presentations we're going to give, or talks. And I'd like your feedback afterwards, but I'll talk about that later. Today, the focus is, let's see if I can get this right, is the talk that Ray's going to give. And obviously we're going to have time for a discussion afterwards. Just to give you a bit of an agenda. Welcome to everybody, and then Ray will do the presentation and we'll have a bit of discussion. And we'll discuss the way forward. What would you like us to do in the next couple of months? Would you like us to give some training courses? What kind of get-togethers you'd like? We'd like any suggestions and comments, and then we'll finish off. So over to you, Ray. Please, before Ray starts, can you switch off your mics and maybe your cameras as well? That if you want to save bandwidth. Okay. Let me see.
Okay.
Sorry, stop. There we go.
I just need to get my peer. One minute, look. I have a young man who is more computer literate than this old man, and I'm trying to get the presentation. Where's the presentation? I want to see my just go to smaller screen. Ah, there we are. There we go. There's the presentation. All right. Close. Now we want to go to start the slideshow. Okay. How do I get there?
Go back there.
There.
Yes, over there. Klik maar net weer en dan klik. Nee, kies die onion.
I need to share screen. Share screen, there.
Yeah, minimize hierso.
Minimize.
En dan klik op daar. Anders. Minimize dit gou hierso, hierdie. Want hy share dit nie nou.
Return to meeting.
Yeah.
Return to meeting. There we go.
Share screen.
Share screen. There we go. Right. Again, let's just by talk 18 receive a pseudo science of a method worth investigating. Just as an introduction over there, is that this started. Magnetotelluric has been around since 1934. It's been around quite a long time. And what had happened is that the Chinese came out with this method without using without measuring the magnetic field. All right, and there was a lot of discussion about this, about the validity of the data and so forth. And but after some library searching, it came out that they tried this in the 1970s and they used it, but they stopped using it for the simple reason that they could not get the sensitivity, because remember, we are measuring the Earth's electric field at a given frequency in nanovolts, as it were. All right, but nevertheless, just the automagnetic telluric signal, generally in the range of 1 hertz to 20 kilohertz. Thunderstorms all around the earth, all right, seismic events and all the rest of it. But the historical audio magnetotelluric is up to 5 channels. You got the electric field, X, Y, X, and you've got the electric field, X and Y, and then you've got the magnetic field, which is X, Y, and Z, the vertical field. All right. Historically, the layout was quite onerous. For 1 to 2 hours for a layout recording. These days, it's gone down to about 20 minutes. Neil Brown, who does most of the work here in Southern Africa, says to me that they're doing stations now about 20 minutes per station, right? But they generally go to CSANT, which is a controlled source. In other words, they're injecting a signal into the ground so that they have a better signal to noise ratio. Most of this data historically has been post-processing. There you have the method where you could have your HX, HY, HZ, your magnetic field, and then you'll have 2 galvanic connectors into the ground at different spacings, all right? 10 meters, 100 meters, depends what it is. And they normally put them in a north, south, east, west direction. But ideally, you would want to be perpendicular upon a structure if you are not in a blank sedimentary environment, where you'd, even with a sedimentary environment, you'd actually want to go perpendicular to any fractures and so forth, because the response is better. Then we can actually see on the right-hand side the plane wave that it is forming. So it is perpendicular to the ground going down vertically, all right? So it is away from the field source, which is in the air. Ignoring that frequency, we're coming back to resistivities of different rocks and minerals. What we have over there is the area that, in the groundwater area that you're looking at, you're looking over there from, in essence, from 1 to 100 ohm meters. That's the area of interest for most cases, all right? All right, and then coming back next, PQWT, basic principles. That's Cagniard's original formula. It's a Frenchman who was a very bright guy. Around about 1961 is his seminal paper. And where rho represents the alternating the alternating resistivity, F is the operating frequency, and the magnetic field and the electric field. You can actually see over there the electric field and the horizontal field are perpendicular to each other each time when you measure it, and you're just taking the square root of that so that you have a ratio, and that is in effect normalizing the data. That we'll come back to later on about normalizing the data. When you've obtained a pseudo resistivity, all right, you would say that the depth is equivalent to a skin depth of the frequency, the resistivity over the frequency, the square root of that times 503. All right, I know CSAMT data uses 365, but you're just overestimating the depth when you'd be doing this, right? Now, we will see later, the magnetic field component is basically stable in most scenarios, small in the area of measurement, and it will be regarded as a constant function of the EX response. So this is where this system really deviates, and the purists are saying, no, but you can't use this at all, for the simple reason is that you are making an assumption of a field that doesn't change. Well, it does change, but it doesn't change all that much. But the live research pulled out Solankas in geophysics, made the comparison between the two methods, clearly outlines the benefits of the telluric method that states that the electronic resistivity was a stumbling block. All right, sensitivity come up over here. So if we're going to have a look at the 1 kilohertz spectra over here, is that you've got the horizontal field on top, you've got the magnetic field on top, and you've got the electric field at the bottom. And you can actually see the response with respect to time. This is over a 24-hour period. You're looking at this as one frequency response. And if I go and smooth this data, we'll actually see that they follow each other to a very large degree. Okay? That is the assumption that you're making. Now, that assumption is allowable at some stages, but other times it's not. As we can see over there, there's also a period of the frequency, and you can actually see that the solid lines is your magnetic field, and the dotted lines is your electric field. The two follow each other very, very much so. Okay? So that is the reason why you're saying that assumption. And it's only let me find it. Sorry. There we go. So if we go put things into perspective, a resistivity, amplitude, or frequency defined constant can work if it's a 1D modeled Earth. In other words, I'm taking a sounding and I'm doing a forward model of that data, and I'm creating a 1D section. Then I'm just I'm moving my electrodes, and I'm doing the same again. So this is a whole series, although the data is visualized as a profile, it is not a 2D profile as such. It's simply 1D sections being grouped together on the spaces. All right? Now, the only time when things really fall off is that between the pi/4 phase angle, the data collection lines should be perpendicular to the structure. When they are parallel to the structure, you start getting really, really bad responses. There's a Magnetotelluric for natural resources over here. This is a manual that we had in 2000, a course that we had in 2007 from Alan Jones, which is very good. In there, there's a paper that really explains that, and I would be putting that on the university's Dropbox for anybody who, instead of having to go and hunt all over for these reference papers, they will be put onto their Dropbox. Right. Zom and Phoenix calculated and displayed. Zom and Phoenix are the two major manufacturers of AMT equipment. All right. There are quite a few others, but by far they are the largest manufacturers. All right. And they actually display the characteristic impedance without displaying the actual E and X. So they take EX and HY, they take the square of that, and all that they're doing, measurements with unacceptable coherency between the magnetic field are normally highlighted in their plots. So they're also doing very much the same. They're taking 1D sections and creating a profile of 1D sections. It's not you can't really, you do join the dots, but you should, theoretically, you should not be joining the dots. All right? The whole thing about this PQWT patent revolves around the signal enhancement, not so much the method. I mean, there are people already building this equipment in Australia in direct opposition to PQWT and another Chinese company that is convenient for me to forget their name. I'm not going to go a lot of people have seen the equipment and they actually use the equipment, but what you have over there, you have your console over there, and that is a touch screen pad, much like a cell phone, also not very visible in the daylight in sunlight. And you have your copper, well, they call them copper electrodes, they're not, they're brass electrodes. and the aluminium on top, and you have the cable, and your separation is always 10 meters. This, because it's calibrated for a 10-meter separation. Now that screen that you see over there, you can actually draw a profile at that point, and there we'll have some data, and we're looking at the data between, this is in a built-up area, this is actually at the factory at Geophysical in Potchefstroom, at the back of the factory, so it's in a built-up area at 11 o'clock in the morning and 11 o'clock at night, so you can just see the repeats. So you can actually see a bit of noise coming in at the bottom over there, but generally the repeatability is the same. So between 1 and 15, there's been 15 readings taken, all right? There's been 15 readings taken. The readings are 2 meters apart. The readings are 2 meters apart, and they're just taking some repeat readings, just checking on the accuracy of the data. Oh, sorry, these were not. These were 1 meter apart. That's a total of 15 meters. Let's have a look. There's the specifications. This presentation will also be on the Groundwater Division's webpage as well. Right. The magnetic field is small and stable. It's in the picotesla range, all right? And using a constant will result in faulty readings only on complex structures. But if you have simple structures where you're going over a dike or a fault or something like that, those assumptions are met, good data can be obtained. We have to take cognizance. This equipment costs $2,000, $3,000. As against $50,000 for a full AMT set. I don't think in the groundwater industry is it justified to go and spend $50,000 on a piece of equipment that may work in some areas and not. You would like to have it. There are a lot of people who have it, but most budgets do not allow for a daily rate of $50,000 equipment, right? Now, again, AMT is built for geothermal work, deep structures, looking at the mow and so forth. But now groundwater and reconnaissance exploration requires a low level of precision to make an interpretation. And you'd want to make an interpretation as quickly as possible. All right, that was just what I alluded to earlier, all right? And in this paper, the difficulty of signal to noise ratios and bandwidth is discussed, which precluded much further work. This is when they just, in 1972, they gave it up until such time that electronics improved. And this is what has happened in the interim period. All right. First of all, this is in the Transvaal series, right? We have a dike on the left-hand side. Then at the top over there, there's a magnetometer reading. Sorry, I did not go from background to background, but I knew that there was a dike over there because it is slightly exposed a bit further down. All right. And then we traversed with the AMT at 10-meter stations. We went into 36 stations. So we're looking at about 170 odd meters, traverse over there. And you can actually see the dike on the left-hand side, all right? Subsequently, at position 9, a drill was put in to 84 meters, all right? A drill was put into 84 meters, and you can see that she is very close to that 90 meters pit. Incidentally, you can see the depth over there, 30, 60, 90, but down to 300 meters. But there was a hole put in over there, and it was made, the yield was 1.75 liters per second, if I remember correctly, all right? So that you can actually see, looking at that data over there on the magnetometer data, you could, and you go and take your half amplitude over there, they're looking at that, you can say that's the edge of the dike, very much the same, right? The next one, we'll just go back to the geology first. This is just west of Potchefstroom, and you have these magnetic shales cutting over there, cutting through there, and there's a borehole over there that was drilled. What we wanted to do, we wanted to actually go either side of the borehole, 25 meters either side of the borehole, and cross that structure. The email that is covered over there follows the sequence over there. You can see that from the magnetic data, right? So there is the borehole that was done. So first of all, a traverse was done from the southerly direction to the northerly direction on the eastern side of the borehole. Then a traverse was done from the northerly side, northwestern side to the southeastern side, 25 meters on the other side of the borehole. This borehole, incidentally, was 2.5 meters a second, 2.5 liters a second. So it was a reasonable borehole. So there on the eastern side, from south to north, we can actually see there. We can see that magnetic shale coming in very clearly over there. The drill point was at point 7. All right. The drill hole was at position 7. Then, after that, from the north to the south, the drill hole position 7, we can actually see that structure going in over there. What is also evident is that we are not quite perpendicular to the structure. If you have a look at the two from the measurements that you can actually see over there. All right. So this was a nice example where you can actually see the structure. All right. You can see the structure and you can go and define where you're wanting to drill. That was the borehole. The next one was in Botswana, and that is a long Maxman line. Maxman electromagnetic equivalence of frequency domain EM system, and that was the line over there, and there was the conductivities done on that line. And the arrow on the top left-hand corner over there, this is the section over here that was redone, all right, with the PQWT. So there it was done with the PQWT. Point 19 was drilled, and they gave it to me in the old. It's an old man like me. He told me that they were getting something like about 25,000 gallons an hour. You can go and convert that. At point 19, they went and drilled over there at point 19 over there. Okay, so there we can actually see another example, east of Francistown. What is done over there is that compared with an AMT system, all right, we're just having a look at the depth, the correlation between the depth calculations for the PQWT and the depth setting. He happened to have a WT 1,500, so you're looking at 1,500 meters depth. All right, this is quite deep, and this is really for basement studies. All right, then the next example over there was, here is a dipole resistivity tomography survey. All right. What had happened over there is that there were 8 dipoles, if I remember correctly. There were 8 dipoles and electrode spacing of 25 meters. All right. So then you're having a dipole from 1 through to 6, and you're doing an inversion of the data, and that's your raw data, that's your inverted data. And if you go and target it there, there's a structure there at 480 odd meters, right? Very clearly sitting over there. And that was redone over there with a PQWT. So there we can actually see the structure, all right? And it was clay to 154 meters, and the total yield was 5,000 liters per hour. It was done over there at that point. So that was done over there at 79, so that was done just at that point over there. All right. This, I think, is a very nice example of comparing the two. you cannot look, going back to here, we're looking at ohm meters, because this is now calibrated. You are converting your response you're converting your response to ohm meters, all right? Whereas over here, we're just looking at millivolts, right? So that is just one thing where this falls down. That's just a close-up of the particular area at 0.9, okay? Not so much groundwater, but here's another system down to 900 meters, all right? And you're looking at a porphyry copper system, and this happened to be in Iran. And the actual structure, there was a core hole down to 1,200 meters, and the structures that can be seen over there were picked up from the core and was picked up from the system as well. And the fault zone was also picked up quite clearly over there. And there's this is the edge of the porphyry system that's coming in over there. So yes, for those that are interested, this is Lichtenberg diamonds, right? So on the top right-hand corner is a Russian radar system, a ground-penetrating radar. You can see there the depth of 50 meters, although it's anybody's guess of ground-penetrating radar looking so well down to 50 meters, but the Russians say they can do it. Then it was done with Edgar Stettler as emeritus professor from Wits, was very sarcastic, and he called it the Tom, but nevertheless, we'll leave it as that. And we can actually see that the first survey was done down to 150 meters with you select your spacings. You can go 100, 150, 300, whatever the case may be. But then I had another special unit that can only look 50 meters deep. The repeat survey was done at 50 meters deep. And if you go compare the repeat survey with the radar, there's a radar over there, and the expected proximate geology model that has come out over there, there is a very, very good correlation of the data. Okay. So, but the initial skeptics have been shown by comprehensive live research that it is an accepted method that fell out of favor due to the lack of sensitive electronics. This is a comment by Carl, who's doing a lot of groundwater system in the Cape. Look at the success scorecard. Just before I go on to unmuting everybody, and I'll take some questions. There were some. Why the two component electrodes? Isn't it just easier for placement of the electrodes into the ground? Copper that is chrome. Stainless steel would be more appropriate. There was a design problem, as I said, that they are brass, all right, and the aluminium handle well in the field. Although they break if you use a hammer on them, you actually need to have a pre-spike to pre-spike and water the holes, because it is galvanic. And where are you looking for water? It's generally in an arid region. So therefore, the surface is also relatively arid. Leave about the choke, that's nothing little. Reading time lows, 1 to 3 minutes is not sufficient for reading the telluric field at any time. This was a purist over there, and at minimum of 20 minutes. Yes, it's 20 minutes with 1980 development electronics, all right? This is now 2020, all right? And electronics have improved quite a bit since then, all right? And nevertheless, there's another thing too, that how long does a reading take? Now, a resistivity section, if you're doing a resistivity sounding, you're setting up your electrodes, your current electrodes and your potential electrodes, and you're putting them out further and further apart. So, and the sounding will be taking you about anything from half an hour to 1.5 hours if you're going down to 50 meters, to 150 meters. Then you'll have about, say, 14 readings. With this system, what you're doing at 150 meters, you're doing 40 discrete measurements where you're looking at that converted to the depth. So in other words, you have a depth range. Although it's not linear, it's the data is given out as a linear function of the depth, all right? But when you're collecting the data, it is not linear. They're just making, they're converting that, that's a pseudo-logarithmic increase in the depth that you're looking at depending on the time. Because in essence, the higher the frequency, the shallower you're looking. In other words, the lower the frequency, the deeper you're looking. That's where the thing comes in, that you're looking from about 10 to 10 to about 10 kilohertz over there for these systems. The one question, the depth estimate for a 1D section using a 10-meter dipole is completely unreasonable. Error in the formula or not. Skin depth formula can apply to the 1D field as it is perpendicular. What I'm saying when I'm explaining that perpendicular is that the into the ground is the source of the field. The plane EM wave perpendicular to the ground, surface away from the field source. So she is going down vertically over there. So whether you have a 100-meter separation or a 10-meter separation, it doesn't really matter. You're still looking below the midway. You're still looking essentially below the midway point. Apologies, I just lost myself a moment. The frequency range. The frequency range from 8 Hertz to about 8,300 Hertz. Note that Zong and Phoenix data collection method is forwarding frequencies in 100 microsecond slices and fed straight into a decon. That's electronics, don't worry about it. There's just the newer system that's coming out from Phoenix is actually working exactly the same as this PQWT equipment, in as much they're staying in the analog domain for longer before they're converting. They talk about resistivity, but in question 6, but if you assume the numbers of the color bar are ohm meters, everything is very resistive. No, the values are not ohm meters, but simply millivolts, low potential equals absorption of signal equals a porous medium. That is what it is all about. All right. Yeah, we're getting a bit technical over there, and the practical unit is 1 nanotesla, posing these. So the answer is 5 to 250 picotesla for the H field, all right? And between 20 and 20 microvolts and 200 millivolts for the E field, all right? So the electronics is 12-bit small signal. I take that from that question, I took it from whence it comes. Confusing your 70s knowledge of electronics with that of 2018. This paper was originally written in 2018. I just want to go back to Pierre. I want to escape. I want to stop share screen. Everybody can come live. Ingrid, would you like to take over, please?
Yes, thank you, Ray. It was an interesting talk. Any questions?
I'm sure there are. Just unmute. Everybody needs to unmute.
Questions?
Hi.
Come in. You have to be there to give me a hard time.
I'd need to go through it, Ray, if I've got to give you a hard time. But the last example, the diamond gravels example that you showed, looked very good. The diamond gravels example looked very, very convincing. The others, so in the one where you compared with dipole, you actually picking up what you're looking for deeper than the penetration of the dipole-dipole, the pseudo section that you showed. So
Correct.
yeah, so it's a little bit iffy. Some of them are a little bit iffy, but I mean, like Gus says, it seems to work. The other thing, of course, is that if you drill a hole in the ground, you're going to find water. So if you bring along a machine which makes pings and you say drill here, you're still going to find water.
But you might find more water.
Yes, no, sure. But what worries me always is just this thing of saying the machine told us where to drill, we drilled and we hit some good water. That you would need to compare it to doing absolutely nothing and, or what is it, looking at
Yes.
Google Earth at 3 o'clock in the morning, like some people are known to do.
Okay, I can answer that question. Is that people who think that geophysics is the alpha and the omega of groundwater exploration, there's a horrible wake-up call for them. It's a discipline, all right, of a lot of inputs, and the geophysics is just one of the inputs, all right, and it just happens to be an input that the interpretation can be difficult. Magnetic data, all right, if you can still use it, because there's where is the largest call for groundwater in a semi-urban area, all right? A lot of times it's in a semi-urban area where you have the noise envelope for your geophysics, for example, just negates the use of a magnetometer in anything but a farming area, all right? Although there are lots of people who use a magnetometer in a built-up area and swear by the data, but we will leave that for the time being. And but the thing is that this is, as they say in Afrikaans, a hulpmiddel, all right? It is an aid to the hydrogeologist or the geohydrologist in his search for a place to drill, all right? And again, if you consider many years ago, you were not allowed to drill a hole without doing a resistivity sounding to go and prove that there is at least something there. Here is another example, is that if I drill over here, all right, something says to me that there's a variance in the structure. I can't tell you exactly what the resistivity of the structure is or the conductivity, but there is a variance, right? And again, it's been used quite a lot in the peri-urban areas, all right? And I say to the people, well, if you think there's a noise component, redo the survey, have a look at the repeatability.
Maybe just then to ask another question is, do you have repeat surveys to look at that?
Yes, we do. Lotte did quite a few repeat surveys. The one survey that I did here is that the survey that was done at 11 o'clock in the morning and 11 o'clock at night. You can actually have a look at the fit over there. And we're looking, and that's it's here in the industrial area. And if you're going to go and put that to a fit, you just need to normalize the data, because remember that the signal is smaller at night than what it is in the mornings. All right? So the signal gets smaller, not larger. Unlike your older, your VLF signals that you used to go and do VLF in the middle of the night, because that's the only time you could get a signal. So yes, the repeatability has been quite good. Raven, you wanted to say?
No, it's fine. I didn't say anything.
Sorry.
Any other questions? Ilana?
Yes, please. Ray, thank you for a
Yes.
very interesting presentation. It's very technical. So I think I have to go through it again to really understand exactly what I looked at. But what I want to ask is, you said that this paper, or this what you presented, is based on a very old technology. So do I understand that the results that you have in the presentation is based on the old technology, or are you using more new technology with what you're currently working with?
There's no ways, thanks, Ilanda. there's no ways that the old technology would have been giving you data like this. This is all the new technology.
Oh,
This is
oh,
what has
excellent.
taken it back into favor, is because they discarded the use of telluric data and they went to controlled source. Well, they left
Okay.
AMT and they went on to CSAMT, which is controlled source audiomagnetic telluric, because the signals were so small and the resolution was not good enough to go and get some decent data. Whereas with the CSAMT, they were getting very good data. Now with the
Excellent.
new electronics, it's coming back and said, there's enough data over there to go and see something because the electronics has improved.
I understand. Thank you, Ray. Yeah, so with other words, it was discarded as an option, but now, because maybe it wasn't so reliable, but now it comes back, and what you're presenting is the results is actually very valid and very, very telling. So thank you. Understood.
Yes. But it's not an absolute value. What you're looking at, everything here is, call it relative, all right? But you're seeing a relative change between a dike and a fracture. You're seeing a relative change between the Botswana example. You're seeing the fracturing in the Mia sandstones quite clearly.
Thank you. Is that Ray? Because you went through the presentation and I didn't see all the slides, but I think I spotted one that looked very interesting. And is that the different reactions with different geologies and different that you actually had there?
Correct.
Oh, excellent. So yeah, look forward to look at that.
The one from Botswana is all in the Mia sandstones, all right? Primarily in the Mia sandstones over there, and you're just looking at the fracturing in the sandstones.
Oh, good. Thank you.
Hi, I've just got two questions quickly. Thank you very much for the talk. Firstly, slide 13, and you don't have to go back to it, but that difference between the day and the night readings, could you just clarify that and what causes that difference? And then my second question is, there's a big difference in the depth that you can measure to. Is that purely dependent on the length of your profile, and what is the maximum length of profile that you can do to get the maximum depth? Thank you.
Right. Thank you, Neville. First of all, you're doing a 1D sounding. Now you're standing at one spot and you're looking 150 meters or 300 meters or 500 meters or 1,200 meters deep at that spot, depending on the equipment that you've got. All right. The equipment, you get 100 meters, you get 150 meters, you get a 300 meters. It's set up for those different depths. All right. The equipment that you buy from both manufacturers, they are generally 150 meters and 300 meters and 500 meters. All right. So that's the depth that you're looking at. So the length of your traverse, the length of the traverse, you're just doing jumps of 5 meters at 10 meters. So your electrodes are 10 meters apart, then you'll do a spacing of 5 meters. You don't want to go much larger than 5 meters, because then you're just looking at a 1D section, 10 meters away, a 1D section. You want to start joining this stuff, all right? And to go and see, and you would be picking up any errors in the reading. If you're just doing a reading every 25 meters, for example, if there is an error on one of the readings, all right, you're not going to pick it up. But if you're going to go take a reading every 5 meters, all right, you're going to be seeing something. Hang on a second. There's a spike in the data, all right, and you can manually, and the equipment actually allows you, you can manually to go and edit out that spike, right? One thing about this equipment, those profiles that I've been showing you are on the screen. You see them immediately in the field, which makes that a very big plus point. You don't have to go back to the office to go and make pretty pictures. So have I answered your question that it's a sounding at different depths. You don't have to do a length, you don't have to do a profile to be able to look deep as you would with resistivity data or with magnetic data.
Yes, you have. Thank you very much. Just the difference between the daily and the nightly temperatures, please.
All right. The Earth expands the same way that a magnetometer, you have a diurnal change of your magnetic field, because the Earth, in the daylight hours, the Earth is expanding. Much the same here, all right? Where we are, all right, where we are at the present moment is that your spherics, especially your thunderstorms and so forth, they happen in the daytime whereabouts you are. So you are concentrated. So you're having the daytime in Africa, but daytime in North America won't affect you so much. So, but there you'll be having more activity. So that activity is spatially situated, and that's basically the reason why you're getting a smaller signal. That also messes around a survey done in the mornings and the afternoons. Sometimes you have to, and you're combining, you want to create a pseudo 3D section, you're having to normalize the data. But that's not a new problem. But with the expansion of the Earth, and you've got more activity in the daylight, is the reason for the change between day and night of your signal.
Okay, other questions maybe? If you look at the chat group, there's 1 or 2 questions there as well, Ray, if you want to look at that. One's about Ricky Murray's.
Where's the chat group? Chat 16.
Just
Is this the chat?
chat.
Here we are. All right. I've got the chat group over there from Derek W to everyone. Are you aware of the work done by Rick Murray in Kucha, Port Elizabeth? He picked up faults in the basement, quartzites, overlying Cretaceous sediments near vertical faults, large throws. No, reminded me to buy him lunch. Okay, that is just a comment more than anything else. I just want to find out if there are any more questions. From Rainy Dennis to everyone, anyone in the group has used this method before and can give an opinion. Is there anybody in this group that has used this method before?
Doesn't look like it.
Doesn't look like it.
Questions from anyone in the meeting?
All right. How many of you are here? 16.
At the moment, we're 32.
Okay, 32. That puts it a little. If a specific area can get together, I'll make available a 150-meter one that looks at a depth of 150 meters, and you're welcome to give me a call next week. I'll give it to you as a demo for a week. You just need to ensure that it is insured for the period that you have it. All right. What I'll do, I'll make available to it is that you pay for the courier to Potchefstroom, from Potchefstroom and back to Potchefstroom, and you just make sure that it's insured. And I'll give it to those people that are interested. I'll give it to you for a couple of days to go and try out. Very interesting.
Ray?
Yes.
I'll speak on Ingrid's mic, otherwise we're getting feedback. just maybe elaborate on the cost of the equipment, because I think that's a surprise compared to other things on the market.
All right. Let's just go back. The first base for a groundwater practitioner is essentially a magnetometer that's been around for many years. Magnetometer costs between 107 and 157,000 Rand at the moment, excluding VAT. An EM34 clone is about 342,000 Rand. I just quoted one the other day. That only looks to 60 meters deep, as we all know. Resistivity system, you're looking at about 100,000 Rand for a single pole system. For a multi-electrode system, you're looking at about starting at about 280,000 Rand. So then we're looking at this equipment over here, you're looking at about between 33 and 45,000 Rand. For your 150 meter one, you're looking at about 33,000 Rand. For your 300 meter one, you're looking at about 38, depending on the exchange rate, of course, as well. And funny enough, the prices between my equipment and that of the oppositions is very much the same. But you can go Google the opposition. I think you need to tell me. And you are looking at about a third of the price of a magnetometer. I think that answers the question over there.
Ray, there's another question on the chat line from Sumaya.
Sumaya, yes, how can you connect for power cables? All right. Your signal to noise ratio goes for a ball. All right. And then when you start getting into a built up area, there is, with the exception of seismic, all right, there's very few geophysical methods that work without the noise taking over. So the answer to your system is that stay away from the power cables if you can. All right. But I do know for a fact that we've done it ourselves with some trials where I actually did a traverse underneath the power line, and this was only one of these power lines on a farm. So we're looking at what, 13 kilovolt, something like that. And and then it was switched off, and then we redid the survey. It didn't see the power line, all right? But when you start getting to your higher power lines, I think you're going to start seeing something. You just have to see it, right? And again, I did mention it earlier. If in doubt, repeat the survey, because remember, you're looking at about 3 minutes to do a sounding. If you take your old resistivity meter, hour and a half to do a sounding, it took you about 3 minutes to do a sounding. So you can do a fair amount of data, and if in doubt, repeat the survey in a built-up area. This is what I'm referring to. I hope I've answered your question.
Hi, hello.
Yes, I see that, Quibus.
Yes, Ray. Sorry, man.
Yes.
Sorry, I was away from my screen when you guys were talking about people that have used it. We've actually used this exact same equipment, the PQWT 300 meter,
yes.
Equipment, and we've actually got quite good results in water supply projects for rural villages and things like that in the former Transkei, and then also for one or two agricultural projects in the TMGs or the Wittenberg group and so on.
Okay, it's interesting that you say in your Table Mountain sandstones that you're seeing something, because historically, I mean, magnetics doesn't work very well in the TMS, and the conductivity contrast is very small in the TMS, so EM was also not working all that well. So it's good to know that that there's a bit of response there for this telluric system in your TMS. Rupert, to everyone, how do you choose where to undertake your survey? Do you run a traverse with a magnetometer first? The answer is yes. I would do that for the simple reason that I'm confirming the strike, the direction of the strike of the structure, all right? Because again, the chances of me getting reliable data is better if I can walk perpendicular. And the same goes for a magnetometer. And then the magnetometer will be picking up the structure quite a bit easier. And we're talking about a magnetometer. You take your reading, you're taking, instead of 3 minutes, you're taking 3 seconds to take a reading at 10-meter stations. So you can do a traverse, you can do a 250-meter traverse, which Henk will tell you as well, is the minimum line length that you should use for a magnetometer traverse if you're going to go and plot the data and you want to do something with the data. All right? So yes, with the magnetometer, you'll see that. But I do know that there are some guys who are saying, but hang on a second, we just take this unit and we go and do 25-meter stations until we don't go and see there is something, and then we go and reduce the stations. Yes, then you're essentially taking discrete measurements at 25-meter stations when you're using the telluric meter to determine the position of that structure that you're wanting to bisect. Conditions where equipment does not work, conductivity contrasts. All right, this is why I said I was enthusiastic when somebody mentioned that in the TMS it was working. And the TMS is notorious for having very small conductivity contrasts. So theoretically, this equipment should you'll have a very, very, very small variation of the signal. This is under which the equipment does not work. Similar signals, inability to penetrate. Well, the inability to penetration is a function of the frequency, right? That is simply a function of the frequency. So you just lower the frequency, the deeper you look. It's as simple as that. Rupert, unconsolidated sands is that by feedback from water surveys in Botswana, from Tony Preston, is that he was using it there in the some unconsolidated sands up there towards Mound, and he's saying he's having some good results. And I also know that it's been used up there in St. Lucia in some unconsolidated sediments reasonably successfully, right? So what has really happened over there is that I was just told that in St. Lucia, he was picking up a perched water table, right? The equipment picked up a perched water table, and I have not seen the data. I was just told that telephonically. So I've had 2 replies, but I've not seen the data, so I can't verify whether it works in the unconsolidated sand.
Okay, maybe one more question.
Yes, I sent in the chat, but I see it's missed a bit. I was looking at the price range from $2,500 to $50,000, and I was thinking is this a tool for water supply or for drilling, for locating the drill sites, or there are other purposes that would warrant you to get the $50,000 one, or what are the other purposes besides these water supply projects?
Geothermal projects, fracking. I see everybody frowning when I mention the word fracking. For deep structural studies, you'd be using your expensive AMT equipment. But this equipment was actually designed for as a groundwater exploration tool.
Thank you.
Okay, any other
Raven,
questions?
Raven, I have been asked that, and I actually put together a document. I will email it to you next week.
Any other questions? Are we done? We'll put all the documents.
Structural mapping. You can use any geophysical piece of geophysical data set to go and do structural mapping. It's horses for courses. Speak to Henk about that.
Okay, are we done now? Thank you, Ray. I really, really appreciate coming. You came in at short notice and you've done an amazing job. It was very interesting and we owe you big time.
Ek soek my wyn. I'm going to go stand in the queue so long.
It's a deal.
On Monday,
it's a deal.
Monday.
We are going to go on, in the future, we're going to have a couple of these things. You'll see on the Groundwater Division webpage, we've already started posting. This is our first one we've done as a northern branch, which is Limpopo and actually northwest, but everybody's welcome. If you want us to do something, if you want us to give training, if you say it's too short, it's too long, any comments, we'd really appreciate it. You can just email it to me. I did on the agenda, my email address is there, so I'd really appreciate it. And then we just want to acknowledge the Groundwater Division. Thank you for this opportunity, for helping us and setting up the Zoom and everything. Thanks, Yolanda. You helped me a lot. And any other comments, questions before we finish off today?
Can I just add something? So I imagine the Western Cape branch will also be running via the Zoom, and I'm sure you guys will also be able to participate, so that it's actually going to evolve into a countrywide participation. It seems like, yeah.
I don't mind. I'm quite happy. The more the merrier, and the more we get to know and the more we learn.
Yeah.
Thank you,
It beats
Ingrid.
the traffic in Pretoria.
But didn't you see, Ray, that's where the next conference is going to be? So, so we better get more used to that when we all get back in Pretoria area.
Most definitely.
Excellent. I just wanted to say thank you so much, Ingrid, and thank you for everybody. I wanted to note that for the people that registered online, we have your emails and you will be receiving the documentation afterwards. So if you haven't registered online, please just add your name to that registration list so you will be able to receive that, because we won't post it directly on the website, but we will post it to all the attendees. Thank you. Thanks, Ingrid.
Okay, any other questions, comments? If not, our next presentation is going to be in 2 months' time. We're trying to do it every second month, and that's going to be on Renee's Groundwater app. Everyone's also welcome to attend that. Otherwise, have a good weekend, and we'll see you again next time.